which the fuel is consumed to generate unit thrust. Right? Otherwise, the amount of fuel consumed to produce unit thrust in unit time. Right? So it is like per second. CT is a thrust specific fuel consumption. So we have W dot from this equation is equals to minus indicates fuel consumed, decrease in the fuel here, right? So W dot is equals to minus Ct times T. So we know dW upon dt, which is equals to dW upon dx times dx upon dt is equals to, so the amount of fuel that is consumed to reach a distance times, or the change in the fuel to travel a distance times the velocity at which you are traveling is equals to minus Ct times the thrust, right? So when this thrust required is equals to, so in level flight you have thrust available is equals to thrust required, isn't it? Thrust available at that condition, at that flight velocity condition. I am not talking about maximum available thrust. So it is about thrust available for that particular flight condition, which is nothing but drag of the aircraft, isn't it? So dW upon dx is equals to minus Ct times T, right, upon V infinity. What is dx by dt? Is nothing but x dot. So we have already defined x dot is equals to V infinity and h dot is 0 for level flight conditions. And we also have T is equals to D, thrust required is drag, and then L is equals to W. Right. So the engine has to deliver the respective thrust. It may not be the maximum thrust that the engine can deliver at that particular altitude. We are talking about a setting, a throttle setting, for which the engine, the thrust developed by the engine is just sufficient to overcome the drag of the engine. That is considered as thrust available at that particular throttle setting. Okay. So this is equals to, so if I want to find out the range for a given load of fuel, what I have is, this implies, so dx is equals to minus of 1 upon specific fuel consumption times V infinity upon T multiplied by dW. Right. So the range is equals to integral from this point at which it started times. So this is the condition, this is the initial condition of level flight, or the distance at which the level flight is started with respect to your coordinate frame, reference coordinate frame on the inertial, or say with respect to your inertial frame, and then the final distance that is covered, final distance up to which this level flight was maintained. Okay, so that will talk about, this is F, right? Okay, so this is equals to minus 1 upon dx, which is equals to integral. So what is the fuel load at which the W naught talks about fuel load at which cruise started, cruise flight is initiated, right? And Wi1 is the fuel load at which after certain time at which the cruise was ended, right? W1 talks about. So I'll write this XL is a distance at which cruise is initiated. Okay. So XF is a distance at which cruise is terminated. Okay. So and then W naught is the initial weight of flight aircraft when cruise is initiated, or at xi. Okay. So W1 is the weight of aircraft, let us say weight of aircraft at xi, and this is weight of aircraft x final. Okay. So the amount of fuel consumed will be W naught minus W1. W during cruise, it's a fuel amount of fuel consumed during cruise is W naught minus W1. So W naught is the initial weight of the aircraft when the cruise is initiated, and the change in the weight is nothing but the amount of fuel consumed, right? So that is W naught minus W1. Okay. So now, so this is nothing but integration of this particular equation. This is minus of 1 upon Ct times. So this I can do it as L upon D, right? V infinity times dW upon W. Okay. Where W is the instantaneous weight of the aircraft. Okay. So here L upon D is because the thrust available at that particular throttle setting must be, if you have to fly in a level flight condition, if you have to like maintain the level flight condition, the thrust available by the engine at that particular throttle condition should be equals to the drag of the aircraft, right? So the drag of the aircraft, which is nothing but thrust required, right? So I multiplied and divided by W, and we know for level flight W is equals to lift, right? So this is L by D times V infinity times dW upon W, right? So if I have to integrate this equation, I have few variables here, right? So let's assume Ct at that particular altitude remains constant, right? Specific fuel consumption at a given altitude remains constant. So you can take it out and further assume that we are flying at a constant angle of attack. So this value is nothing but E, right? Isn't it? So minus of 1 upon Ct times, so W naught till W1. So L upon D, which is nothing but E times V infinity times dW upon W, where W is the instantaneous weight of the aircraft. Okay. Now, if you maintain a particular angle of attack, which is true for cruise, right? Because L by D remains constant because CD is a function of CL and CL is a function of alpha. When you maintain a particular angle of attack, so L by D at that particular alpha remains constant, right? So for the cruise flight condition, L by D is constant. Now you have either two flight conditions. One is V infinity, right, is again a function of density here. Am I correct or not? So whether are you ready to allow this aircraft to fly at a constant altitude, or are you ready to make this aircraft fly at a constant velocity? So let us discuss what it is exactly. We have L is equals to W, right? Isn't it? So half rho V square is CL is equals to W. Okay. Isn't it? So for a constant angle of attack for cruise, CL is constant, right? So as we progress in our flight, the weight of the aircraft is decreasing because the fuel is consumed in the level flight condition, isn't it? So as the fuel is consumed, so if you are maintaining, say at a given altitude, if you are maintaining a constant velocity, assuming CL is constant because alpha is constant here, if you are maintaining a same velocity throughout the flight, that means there is additional lift generated, right? So there is some force, additional force which is generated. So there is an additional force here, right? Because there is a decrease in the weight of the configuration because of the fuel consumption. So there is additional force which makes it to start moving upwards, just like a balloon, right? It may not turn up and climb, right? Because you are not deflating the elevator. So you are not changing the orientation, but it may start raising up, right? So that means the only way it can change is like decreasing the altitude, right? Isn't it? That is how it can balance, right? So as the height increases, the density decreases. If I increase the altitude, if the aircraft increases its altitude, the density decreases. Hence, even if you are not touching the throttle, so this V infinity may say still be the initial V infinity with which you have initiated the thrust, the level flight, and then if you if you still maintain that V infinity same as the initial value, right? So the density has to decrease. That can happen only when you start increasing your altitude, right? So the aircraft starts gaining altitude, just like buoyancy. No? So if you have a gas balloon, if you leave it, it will slowly starts gaining its altitude, right, until the density is equals to the pressure difference inside and outside is equals to same. Otherwise, it will start. It will start increasing its altitude. So similarly, this happens until the density decreases to a level where the force, the lift generated at this particular flight velocity, which is same as the initial flight velocity at which cruise is initiated, and you are maintaining a constant alpha. So let's say the pilot sleeps in between. There is no autopilot, right? So he has set the flap condition, elevator condition to a certain, by means of a trim tab. He trimmed the aircraft elevator to a particular angle, which reflects in the angle of attack. Now the pilot slept, let us assume. Okay, so that means the CL is constant and he is not touching the throttle. So what he realizes after a while is he has gained some altitude. Okay, that's because the fuel is getting consumed, you are not controlling the velocity. So this is like constant density or constant altitude flight, right? So if such a so either it's not a constant altitude flight in that case. You can either force a constant altitude flight or a constant velocity flight. Here it's a constant velocity flight where the altitude is allowed to change. The aircraft is allowed to move up, right? To change its velocity. Sorry, to change its density. But in the other case, let us say I want to force the level flight, right, at a constant altitude. Then what I need to do is to change the velocity. I need to continuously change the velocity, decrease the velocity so that the total lift generated is equals to the weight of the aircraft. Okay. So now if I consider constant velocity, right, maximum range when, or say if I have to solve this equation, I need to either consider constant altitude or constant velocity of flight. So let us now solve for constant altitude, right? So constant range altitude, range of a jet engine, right, with constant altitude. That means you are varying the velocity here, isn't it? So what it mean? So R range is equals to, so minus, I am taking minus into this integration, which is equals, so changing the limits of the integration, right? Because W0 minus W1 will be positive, because W0 is higher than W1. Okay. So which is 1 upon Ct times CL. I can take 1 upon Ct outside of this integration. So CL by CD times V infinity is root over 2W times rho S CL times dW upon W. Okay. So for a constant altitude range, I can take density constant, consider density constant, right? I can take it out of the integration. So what I have is 1 upon Ct times root over 2W by, root over 2 upon rho S can come out of this integration times CL power 1 by 2 within the integration times CD, okay, CL power 1 by 2 times CD multiplied by dW upon W raised to the power of 1 by 2, okay, or root over W. So this is from W1 to W0, okay. So this is what the integration turns out to be. Now, if you are, since in the level flight you maintain angle of attack constant, so CL power 1 by 2 by CD will remain constant. So it will come out of the integration. So the range is equals to 1 upon Ct times root over 2 upon rho S multiplied by CL raised to the power of 1 by 2 upon CD times. So 1 upon root W is W power 1 by 2 root W, which is root over W0 minus root over W1 upon 1 by 2, that is like 2 upon Ct naught, 2 upon Ct, isn't it? 2 upon Ct multiplied by root over 2 by rho S, CL power 1 by 2 by CD multiplied by this factor. This is the range for constant altitude. So note it down, this is a range for constant altitude. Okay. So if you consider constant altitude, this is what the range that you are going to get. You allowed the velocity vary to vary during this level flight condition, right? So, okay. So when this is maximum, so the range is maximum, range maximum for constant rho, okay. Range is maximum for constant rho when 2 upon Ct times, so root over 2 by rho s times Cl power 1 by 2 upon Cd. This has to be maximum, isn't it? That's the only variable here. So this has to be maximum to have this range maximum, root over W naught minus root over W1. So d by dCl of Cl upon 1 by 2 by Cd has to be 0. That is when we can get Cl is equals to root over Cd naught upon 3k and Cd is equals to, so 4/3 Cd naught, I guess, isn't it? Okay. So these are the two conditions for this maximum range. If you substitute this value here and Cd value here, so you will get what is the maximum range at constant altitude. So what will be the corresponding velocity for Rmax? Rmax when rho is constant. So this will be root over 2W upon rho s for Cl for Rmax when rho is constant, okay, which is equals to rho. So this is the corresponding thing. Cl when Cl power 1 by 2 by Cd is maximum. So that is 2W upon rho s times root over k upon 3k upon Cd naught. Okay, this is the corresponding flight velocity. So this is for constant altitude flight, right? We force the jet aircraft to remain at the constant height. So let us say if we don't force that, if we allow it to change its altitude, but we force the velocity to be constant, okay? We force the velocity to be constant. So what we can say is, then the range is equals to, so in this particular integration, where r is equals to 1 upon Ct times integral over E W naught to W1 to W naught E times V infinity times dW, isn't it? Yeah, by W, dW upon W, sorry. Okay, so if I consider this for the, like if I take V infinity constant, so L by D is constant, we know that, isn't it? L by D at a given angle of attack is constant, that's the assumption we have. And Ct at a given altitude is constant, right? So range is equals to, so we don't consider the Ct variation, we assumed it as independent of altitude here, right? That small change in the altitude. So 1 upon Ct times E times V infinity times, okay. So this is ln of W naught upon W1. So this is greater than 1. So this exists, ln exists, and then, yeah. So then it's a positive quantity. So what we have is 1 upon Ct E times V infinity. So this is the range equation for constant velocity. So this is for constant velocity. Constant velocity range for a jet aircraft. So this is also known as Brigot range equation. So Brigot range equation. So the maximum range that you can achieve from this Brigot range equation is when E is maximum. When E is maximum, this becomes V infinity becomes VR, right? Isn't it? So that is when it can happen. It has to become maximum, this value. So this value turns out to be VR. So Emax, okay, times VR times ln of W naught upon W1, where Emax is 1 upon root over 4k CD naught L by D max, and VR is root over 2W upon rho S times CL star, and CL star is root over CD naught upon K. Okay. So this is a corresponding maximum range, Brigade range equation. Okay. So when you maintain a constant velocity, you allow the aircraft to change its altitude. So this is the maximum range that you can get with a load of fuel. Okay. Yeah, let's solve for the endurance of this jet aircraft. Okay. So we now solved for the maximum range with a given load of fuel now of a jet engine. We have two solutions. One is constant velocity and other one is from the constant altitude. So constant velocity occurs if you the maximum range with the constant velocity occurs when you fly at or you trim at an angle of attack which is at L by D is at which L by D is maximum. And then when you want to fly at a constant altitude, then you need to fly at an angle of attack where CL upon C by 2, CL raised to the power of C by 1 by 2 by CD or root over CL upon CD should be maximum. That happens when CL is root over K upon 3 CD naught and CD is equals to 4/3 of CD naught, right? So that's a condition, and you also figured out the corresponding flight velocity. Now we are talking about with the given load of fuel, say if I want to stay for the maximum time, right? That is nothing but the endurance. What will be the endurance of an aircraft, right? Endurance of jet aircraft. Okay. So similar to that, what we solved for glider. Right. So what we have is the endurance, which is again we have specific fuel consumption. Ct is minus W upon dH. Sorry, T. And then what we have is dW or say W dot, right? dW upon dt is equals to minus Ct times T. So dt is equals to minus 1 upon Ct times T, Ct times say L upon D times dW upon W. Okay, since lift is equals to weight here. So this is nothing but dt or T endurance, or T is equals to endurance for jet engine, which is T, which is equals to integral over dt from Ti to Tf is equals to Ti is the time at which the cruise is initiated, Tf is the time at which cruise is terminated. Okay. So this equals to minus 1 upon Ct times integral W naught W1. So the weight of the fuel, weight of the aircraft at Tf, W1 is weight of the aircraft Tf, and W naught is the weight of the aircraft at Ti here. Okay. So is 1 upon Ct times E times dW upon W. So at a constant, for cruise at a constant angle of attack, what you can say is you can take E out of the integration for constant angle of attack. Okay, what you can solve this equation for T, which is equals to E upon C 1 upon Ct times E times ln of W naught upon W1. Okay, where again Wf is W naught minus W1. Okay. So this endurance of this jet engine is maximum, will be maximum when E is maximum, L by D is maximum. It's independent of here. We don't have any flight velocity or density coming into the picture here, right? So if you want to fly for maximum time with a given load of fuel with a jet engine, what you need to do is you need to fly at L by D maximum. So T max will be 1 upon Ct times E max ln of W naught upon W1. Okay? So where E max is equals to, again, I'm not writing that again, right? You know this, E max is 1 upon root over 4 k Cd naught, and the corresponding velocity will be the same velocity here. Okay. So this is the endurance and the maximum endurance of a jet aircraft. So we now completed what is the range of a jet aircraft as well as endurance of a jet aircraft. Okay. Now we'll talk about range and endurance of a propeller driven aircraft. Range of propeller aircraft. Okay. So again, we have discussed about for a propeller aircraft, we talked about generally a reciprocating engine, right? We talked about specific fuel consumption, right? So here it is thrust specific fuel consumption. There we talked about specific fuel consumption, which is power specific fuel consumption, C, which is equals to minus of W dot upon P, right? So this P is nothing but unit power generated by the engine, which is nothing but, what is the power generated by the reciprocating engine? It's a shaft power, right? So this, we need to understand that this is shaft power minus W dot upon shaft power here, okay? So where propeller efficiency is equals to power available upon shaft power, okay? So if you want to talk about the performance of the aircraft, then this power available has to be equal, should be equal to drag times velocity, power required by the system time, right? Shaft power, so shaft power is equals to drag times velocity upon propeller efficiency. Okay, so substituting that here, what we have is dW upon dx times dx upon dt is equals to, so this is equals to minus of C times d times V infinity upon propeller efficiency. Am I correct? This is shaft power multiplied by shaft power, which is nothing but power available upon efficiency. Power available is drag times the velocity. Sorry, which is must be equals to power required for the level flight condition at that particular velocity. So which is nothing but thrust required times velocity, which is drag times velocity, right? So this is minus C upon eta P multiplied by dV infinity upon V infinity. Am I correct? So what I want is the range dx is equals to minus of eta P upon C 1 upon D times dW. So this is like L by D times dW upon W here. Okay. So I don't see any complexity in this equation for a level flight at a constant alpha. So the range is equals to R, which is equals to integral over dx from xi to xf, right, which is equals to minus of eta upon c integral, okay, assuming constant angle of attack, yeah. So which is true for level flight. So from W naught to W1 dW upon W. Okay. So the maximum, the range occurs when E is maximum, isn't it? This equals to minus eta upon C, or say eta upon C, specific fuel consumption times E times ln of W naught upon W1. Right, so this is our range equation, or say R is equals to, so eta C multiplied by, or R max, that is our range equation. The maximum occurs when E is maximum times ln of W naught upon W, where E max is 1 over root over 4k CD naught, and yeah, and the corresponding velocity for this is V for R max for a propeller driven aircraft is root over, this occurs when L by D is maximum, right? So 4th root over k upon CD naught. Okay. Okay. Fine. So let's now figure out what is the endurance, right, of propeller aircraft. Okay. So let's now talk about endurance of the propeller aircraft. With a given load of fuel, let's look at how long I can stay in air, right? So that's the endurance. So we know again from the definition of specific fuel consumption, we have dW upon dt is equals to minus dW upon W dot is equals to C times dV, isn't it? Drag into velocity. So if I want to find dt or the maximum endurance, so I am trying to rearrange this equation. So which is eta of the propeller times C, right? 1 over d into V infinity times dW. Okay. So this equals to, so the T is integral over dt from Ti to Tf, which is minus eta upon P, eta P upon C, integral over W naught to W1, right? So 1 upon dV times yes dW. So let me just, I am multiplying it. Okay. So you have L by D E, right, at a constant angle of attack. This is constant. So just try to write this equation in a better form. Yeah, let it be here. Let it be as it is. So again here we have V infinity into the picture. That means either we can force a constant density flight or a constant velocity flight, right? First look at what is constant density, which is constant altitude flight, right? So let's say endurance. Okay, no need to write it again. So at constant altitude, we allowed velocity to vary, right? So let's now remove the variable from this integration. We try to change it, this velocity in terms of CL here, right? So what we have is the endurance T is equals to, so we assume the propeller efficiency is not changing with velocity of flight, right, upon specific fuel consumption. So this is W1 to W naught, changing the limits of integration by taking minus into, and then what I have is CL upon CD and changing, so which is W is 2W root over rho S, which is CL power 3 by 2 times 1 over root over rho S upon 2 multiplied by dW by root W. Okay. So for a constant altitude flight, this is what it is. So for constant altitude, this particular parameter, or say this particular fraction is constant, isn't it? Because density is constant, and we have CL and at a constant angle of attack, CL and CD, or CL power 3 by 2 by CD is also constant. So you can take it out of the integration. What I have is T is equals to eta of the propeller, efficiency of the propeller times CL power 3 by 2 upon CD. We can keep it as it is, rho S upon 2 times CL power 3 by 2 by CD multiplied by 1 over integration of 1 over root x, right? So this is like x power root x, it will be root x, 2 root x, right? Isn't it? 2 times root over w naught minus root over w1. Okay? 2w, isn't it? 2 root v infinity is in the denominator. So I multiplied it by w. Asha, so there is a mistake here. Please make a correction. So this is, so we have a w here, isn't it? So 2w multiplied by rho s times w raised to the power of 3 by 2, right? Isn't it? So please make this correction. So t is equals to, which is 3 by 2 minus 3 by 2 plus 1 will be minus 1 by 2, right? So 1 by 1 by 2 it becomes by 1 by 2, right? So this will like, this we can take it out of integration rho s upon 2 times CL power 3 by 2 by CD multiplied by, so 1 upon root over W1 minus 1 upon root over W naught. So since W naught is higher, this term is smaller than this particular term, so this quantity still remains positive here. Okay. So at a constant altitude, this particular parameter is constant, we took out of the integration, and we are talking about level flight, making it fly at a constant alpha. We are not touching the throat elevator there, right? So we are not changing angle of attack, thereby maintaining a constant angle of attack. So which means thereby maintaining a constant CL and thereby CD, right? So this equals to 2 NP by C root over. Okay. So when can this be maximum? For at a constant altitude, this can be maximum when this CL power 3 by 2 by CD is maximum. This is maximum when this is maximum, and the corresponding velocity is, velocity for T max is equals to root over 2W by rho s, 2W by rho s times root over k upon 3 CD naught. Okay, meters per second. This is the corresponding velocity that you have to maintain. Okay. Now let's also solve for constant velocity endurance, or say endurance with constant flight velocity. What is that? T is equals to eta P upon C integral of W naught up to W1 times E 1 V E times 1 over V infinity times dW upon W. Isn't it? So if velocity is constant and we are maintaining constant angle of attack, so this comes out of integration. It's a straightforward integration. So what we have is eta P upon C is like E times VR, right? Or say velocity V infinity times ln of W naught upon W1. This is the endurance of propeller driven aircraft when you are flying at a constant velocity. You allowed aircraft to gain altitude, right? So we'll also solve for, say, what happens when the aircraft gain altitude, right? How much altitude does the aircraft gain during a cruise? That is what we call it as cruise climb, right? When you are allowing the altitude to change, that means you are allowing it to so density to change, which means you are allowing the altitude to change. So there is a gain in altitude even in cruise when you are flying at a constant velocity. So we'll also figure out what is that gain in altitude. How much altitude will be the difference over a range, range of flight or over a tank of fuel. Okay. So this is maximum when E is maximum and V becomes VR, right? Ln of W naught upon W. Okay. So I am not again writing what is VR and Emax, which you know very well. So okay. So this is what we are supposed to, like I plan to discuss in this particular lecture. So what we started with is range of a jet aircraft, and then the propeller, range of a endurance of a jet aircraft, where in the range we saw that it has to, like there is a constant velocity range as well as constant altitude range. So we also got a Breguet range equation there, and we solved it for the maximum conditions as well. And then we started the propeller driven aircraft, what should be the range with a given load of fuel. So we have solved for the range as well as the endurance for the propeller driven aircraft. So range is straightforward there. We don't have, so it can happen at L/D maximum. So but for endurance of this propeller driven aircraft, again we have two flight conditions we need to take care of, either a constant altitude or a constant velocity flight. So constant altitude flight will end up you flying at power required minimum condition, right? That's for the maximum range, so you need to fly at power required minimum condition for a constant altitude. But if you allow altitude to vary, then you need to fly at a constant velocity, right? So which is again corresponds to L/D maximum condition, right? Drag is minimum here, that corresponds to drag minimum condition. Okay, so with this I would like to end this particular topic. So next time when we discuss, we'll start with what should be the, as I mentioned, we'll talk about what is the height gain during this, and then we'll slowly progress towards climbing flight, and then yeah. Thank you.